Good day to you from Anagalactic. Today we'll be presenting a non-Euclidean geometry, and the word Euclidean can be exchanged for linear geometry to advantage. Euclidean is kind of outdated. Linear is more straightforward, since it is the geometry based on the straight line. The use of the word line is confounding in a sense we wish to disambiguate just to be sure of our terms. It is used in two different ways. The typical use when you say line is you mean a straight line, so you don't need to say the word straight. But then when you refer to a circle, it is a kind of line, but it's not a straight line. So can you say it's a line at all? Yes and no, and that's, I think, an interesting way to be able to say it. It depends on what you mean. When you say a straight line, you mean a line with no curvature if you're including the curves as lines. So if you do include the curves as something you can draw in the same way that you draw a straight line, then a straight line is a special case of curvature. And that's the most advantageous and concise and correct, finally, way of organizing our use of the word line, since it has a hierarchy with respect to curvature. What you're seeing over here is a plane, a planar image, which is it looks like it's encased in a circle, but it actually goes on for infinity if you wish to unbound it. And on the surface of this plane is a grid and another set of lines. So the grid is the vertical and the horizontal axis, called the x and y axis, making the plane squared. It turns the plane into squares, which is actually why we have so many squared terms. So that's the plane. The plane is a very important object which Euclid implicitly began with, but did not explicitly state that that's what he was starting with as his surface, because it was simply assumed by the Greeks, because that's where you draw straight lines, is on a planar surface. But if you want to use coordinates on the surface, you need two lines. Basically, you would say it's planar longitude and latitude. What are the two aspects of the plane? This way, horizontal, and this way, vertical, make squares, which, in a sense, encompasses the whole plane, but not to infinity, unless you wish to say that that space, which would be the universal space of your geometry, had a square edge, which we don't usually think of space that way. It has a spherical edge, the way we see. But another way we see, without the use of depth, is a flat screen image, which actually physiologically we do see. And that's easily provable to yourself, especially since you're looking at a flat screen image now, and you cannot tell the difference between that and reality. There's a footnote there, but actually you can't. So we have a plane, which is very important because it's how we see, but we also have depth vision, so we need to take that into consideration as well. We cannot do so on a planar surface except by projection. And the use of the sphere on a planar surface is done with shading and using an ellipse to draw the equator, for instance, whereby you gain visual clues that that's meant to have depth. But on a planar surface, of course, in a sense, that's illusory. Very interesting aspect of vision. So what you're looking at here is a superposition on a plane of a Cartesian grid and radial spokes, which you could say could be measured using the Cartesian system, which is a coordinate system for that space. So that's in a nutshell. This is formal, but I do want this to be entertaining as well and not tedious. But it is necessary in a formal sequence to be absolutely precise. And now we're going to do something interesting that apparently nobody has ever thought of doing, or if they have, it has been considered to be worthless either to themselves or whoever saw it, and it perished from science, which is quite simply the transformation of one unit circle into its reciprocal, which is the same unit circle, except instead of having one on the radius, which is called the unit circle, you transfer the unit, which is 1, that's what is meant by unit, you transfer that to the circumference, which can be done on a simple mathematical formula. That 2 pi r equals capital C, that's the circumference, so the relationship between the circumference, capital C, and the radius is that if you multiply the radius by 2 pi, you'll get the circumference. Meaning that if the radius is 1, then the circumference is 2 pi. Now we all know that from school. But you can invert that. You can actually take the 1 that has a relationship to 2 pi, which is the linear value of the circle, which is kind of a strange thing to say, since a linear value only makes sense on a line, which is why 2 pi is irrational, essentially. So all of that is, I would say, fairly well known, although not usually explicitly drawn out that way. Irrational numbers are a peculiar class of numbers, and they're infinitely dense on the line. When you unitize the line, you're not recognizing those irrational numbers, but instead you're using a rational number for the linear distance. That is, linear spatial separation is the metric of the line. That's what it's used for. It's for measuring distance in what? In space. On what? On a line. So it's a line in space. But in geometry, it's a line in 2D space. So if you want to get a coordinate on a line, it's not a coordinate. It's a single number. So a line only has one component numbers. That's the official, you could say, qualifying term. The line is composed of single component numbers, which seems redundant until you consider, is there such a thing as a two-component number? There is. One example of a two-component number system is the complex number system, which I've given several lectures on, basically for that reason, is to show you the power of two-componency in a number system. The number system we use, the linear number system, based on the line, is a one-component number system. 1 plus 1 equals 2. Each one of those three numbers is a single component number. And you can add them, and that's all you can do. That's the only operator that works on the line. Now, that is not what is commonly taught in school, but it actually can be proved. So I did prove that, and so that's the operator for the line. You might say, what happened to subtraction? You don't need it, and you can prove that to yourself, and that'll be homework for you. You learned it in school at one time, but you may have forgotten. So there's no such thing as subtraction, unless you want it, because all it is the inverse of add. But that's not used for distance. You don't use subtraction, and the Greeks did not use subtraction. They used addition. If they did use subtraction, and in fact they did, it had to produce a positive number. You can subtract one positive number from another. 5 minus 3 equals 2. Perfectly fine. It's essentially the inverse of add. Instead of adding one number to another, order is important though in subtraction. In addition, we say that that's commutative. That 1 plus 2 is the same as 2 plus 1. But 2 minus 1 is not the same as 1 minus 2. And the reason I said that the Greeks didn't use subtraction is because they didn't need it. And if they had tried, they would have, as I'm sure they did, they realized that that's a ridiculous thing to do, because eventually you'll get 1 minus 2, which is ridiculous. Because they had no negative numbers. They also did not have 0. So they thought that all numbers were supposed to be rational, at least up to a certain phase of the history of geometry in at least Greece, that all numbers were supposed to be rational. Well, when they came to the circle, they found an irrational number. If you're trying to measure the distance on a circle, you can't. It can't be done because it's not a distance. There's no such thing as distance on a circle. Now, we're taught in school that you can take the equivalent of distance on a circle, called the circumference or an arc of thereof, which is the same thing as a line or a segment thereof. And that makes sense to us, except for the strange fact that it's curved. So it's not a linear quantity anywhere on the circle. It's a coordinate quantity, a two-component number. And that's why when you get a point on a circle on a plane, it does not have the same data type as a point on a line. So that's condensing a lot of information. I hope all of that made sense, but again, this is formal, so I do have to be just a little bit temporarily tedious, but I do try to keep these videos entertaining as well. And a scientist experiences no form of entertainment higher, besides the beauty of God's creation itself, which is why we do science, in one human sense, is a discovery. Something you didn't know before that may have value. All new knowledge has potential value. So what did I discover, or what's our next step? What are we going to do? We now have the unit circle, which has a radius of 1, and therefore it has a circumference of the number which you could call tau, but it's too late to change. It's 2 pi. And 2 pi occurs in every single equation in top-level physics. 2 pi is peppered all over everywhere. 2 pi is everywhere. Because when you have a radius of 1, you have a circle which has a value. You should just say it has a value of 2 pi. So that's quite simple. But if you would like to have a value that is rational for the circle, you have to invert the system, which is easily done on a formulaic conversion, because the ratio between the radius, which is obviously smaller than the circumference, in equivalent units for curvature distance, which is not linear distance, it's curvature distance, which is not distance. But you can pretend that it is, but it's not. It simply is not. That is not a distance. Distance is not measured on a curve. Distance is defined on a straight line. It has no context off of the straight line. And the same is true of well, I don't want to confuse the issue, so let's leave it at that. That's enough heavy-duty stuff there. I don't want to go too fast, but I also don't want to get bogged down in details. So if you do have a unit circle, which is used commonly, it's considered to be rather a holy object, because if you have a unit on the line, which is where it belongs, which is the radius, that has a fixed, constant mathematical relationship to the value of the circle, which is about 6 1/4 times bigger in equivalent units on the curve, which is the circle. I have to keep repeating this to make sure that you know the difference between the two number types. A number on a circle is not a linear number, which means it's not a one-component number. It's a coordinate number, x, y. That's the value of a planar object, such as a circle, or a square, or a triangle, or anything you can draw that's, not strictly speaking, just a straight line, but is an object. Any point, any position is what you should say. Any position, really in the whole space, or any object thereof, will be a two-component number, because you need two components. You need two numbers to fix the position. One number will only give you the horizontal aspect or the vertical aspect, but you have to have both, and that produces squared space, which is why, essentially, why we have so many squared terms. And we'll be getting to C squared as a case example of how you can decompose that using this new geometry, which is highly instructive for E equals mc squared. It's one of my most popular videos. So we're getting to that. But this is just the basic approach to a very simple transformation where we now have a new kind of unit circle, which is no longer linearized on the radius, but is rationalized on the surface. A circle has a surface, a line does not. That should be obvious. So the circle has an interior, a line does not. You could say that the equivalent of the interior of the line would be any point on the line. But in the case of the circle actually encloses space. So it has an exterior and an interior, and the boundary between the interior and exterior of the circle, as you can see on this diagram, for example, the red circle has an interior, and it has an exterior going out 2, 3, etc. But it also has itself, which is considered a surface, and that is nonlinear. But you can see that there are two lines that go through the circle. So these are superimposed parameterizations of the plane. You can either circularize the plane, although nobody ever has, although you can draw it. Normally what you do is you draw the x, you draw the y, this makes squares. And when you go to 3D, you now have cubes, and that's what Einstein used to make space-time. He made hypercubes. That's simply a tautological fact. So we don't want that. We want to see what we can do with circles instead of squares. But the two parameterizations are superimposed here, and that's actually one of the correct usages of the very powerful word superposition. There are two superimposed, you could say grids, but only one is a grid, the Cartesian grid, with which we're all familiar, x and y. So that's one way to be able to get any position, is with a combination of x and y. Called the Pythagorean theorem. You take the square of one side of a right triangle and the square of the other, add them together, and now you have to do the square root, which is where the whole system falls apart, because now you get another irrational number. So that is what we're taught in school. That's what Einstein used, was the Pythagorean theorem. But then you do have to take the square root of the sum of four squares, one of which is time. And so it comes out to x squared plus y squared plus z squared minus t squared. It has to be minus, otherwise you just get a tesseract. But what he wanted was to be able to hyperboloidize space-time, which he did, and now it's considered to be pure magic, just pure genius. There is a huge flaw in his system, and we'll be getting to that. So we'll also be dealing with the Einstein field equation as well as the Einstein energy equation, both of which can be rewritten in circular geometry using a circular number system, which we're getting to. So now we have two unit circles, which are inverse of each other, and the multiplicative inverse relationship is called reciprocity. They're reciprocals. So if you have a unit circle with 1 on the radius, you can invert that. And let's do so. It's a very simple formula. We want 1 to be the value of the surface. We want the circle to have a value of 1. And there's an interesting twist there in what I just said, but I won't introduce that now because it might be distracting. But actually you have two different forms of 1. If it's a 1 on a line, as it would be for x and y, it's a single component 1. But if you say that 1 represents the circle, which is not a line, it has to be a 2-component 1 because it's a planar closed object. And so it requires two numbers. A single line is an incomplete portion of the plane, and each of the two lines, which are orthogonal, each have a 1-component value. But for a position on the plane using that xy system, you need to somehow conjugate the two numbers in order to produce another single component number. Am I correct? No, I'm sorry. You need a 2-component coordinate position. You need the x and y value. So a position on a line would be 1, 2, 3, or 4. But a position on a circle will be 1, 1, 2, 2, 3, 3, 1, 2, 3, 1, something like that. This much x and this much y, each of which are linear numbers. But the circle cannot have a linear number because it's not a line. Only a line can have a distance. Only a line can have a single component representation. If you're using linear numbers, which we do, then you need x and y. That's called a coordinate. You can think of it as latitude and longitude on a flat surface, which, as you can see, can be superimposed on a circular surface, which now you can see is a projection of true latitude and longitude on a spherical surface projected down to a plane. Now that's a lot of information, which is simply to emphasize that linear numbers are single component numbers that add. But coordinate numbers are two component numbers that don't add. They don't add. You can't add one coordinate position to another to just get a distance, because there's no addition to do, because they could be anywhere. That may be stating it a little ambiguously. Let me be more clear about that. Since a position on a plane has to be a coordinate number, because the plane is not the line, but is it the composition of two lines? It is if you use the XY overlay, called a superposed grid. It's not the plane itself. We're taught the Cartesian plane, I think just a little bit misleadingly, as if that were the only way to get a position on the plane. In a sense it is, because you do need two linear numbers. But the way it's done with the Pythagorean theorem is with add. You add two squares and then take the square root. That's fairly easy to say, but it's not very easy to do. To square a number is not difficult. That's an ordinary, it's just a special case of multiplication where the two multiplicands are identical. So we call that a square, but it's simply multiplication is all. But it's coordinated multiplication where x and y are the same, which is a special case. So all of this is to say, single component numbers do not represent positions on the plane. They only represent positions on one of the two orthogonal lines. So all of that is to state the obvious, but now comes the powerful part. Since we know that any position on the plane has to be a coordinate position, you need two linear numbers. Is there a way to combine them? The Pythagorean theorem is the answer if you're using the operator of the line, which is add. Essentially, instead of adding two numbers to get another number, you square the two numbers to get both aspects in coordination, and then take the inverse of the multiplication, which, since this is the square, which is a very interesting form of multiplication since the two numbers are the same, we give a special name to the square root, which is if you have that single component number resultant from the addition of two single component numbers. Each squared number is a single component result. So x squared plus y squared is simple addition. But then the result that you get is a square number. And so therefore you have to take the inverse of multiplication to extract what is called the root of the square. And that would be the inverse, whereby the number that you get would be the number that is identical in both multiplicands. For instance, 4, if you take the square root, it's 2 because both numbers are the same. So that's how you take the square root. You're finding the two components of the square, which you already know are going to be the same linear number. That's the value of the Pythagorean theorem, is you're assured, based on the rule of multiplication, that both numbers are going to be the same. That's why the square is such an important number. The square of a number is because you can then add those quantities and then take the inverse, which is strange because it's a combination of addition, multiplication, and finally a special form of division, which is saying a lot, but that's really what it is. And the rub is that the square root function is transcendental, very similar to the calculus computation, neither of which is precise, which alarmed the Greeks. Like, they didn't like irrational numbers. So what we're doing is taking the irrationality of the relationship, which is normally the 2 pi on the surface, and we're making the surface rational, and thereby, on the reciprocal, making the radius of the circumferential unit circle the inverse of 2 pi, which is 1 over 2 pi, which is approximately 0.16. So this red circle, if that 1 right there that I'm pointing at, if indeed I'm pointing at it, let me make sure I have my... Where is that? There it is. So now you can see, I trust, my pointer, which I'm flailing around here. There. That 1 really on this graph shows the radius of this red circle, would thereby be the unit circle. But if we change that 1 to refer to the red circle, then the radius is 1 over 2 pi, a very simple mathematical formulaic transform. So we can do that. That's a constant relationship, and we simply inverted it in order to put unity onto the object, off of the radius and onto the perfect curve. The closed line, the circle, now has a rational value. But is it in the correct form? No, because it's not a coordinate number. Since the circle is not a line, but rather a planar object, whereas the line is not a planar object unless it's in relation with the other aspect on orthogonality. The circle has no need of orthogonality, and that is a profound statement I just made, which I've never really said out loud even to myself, but that is true. So the true value of the circle, you can say it's 1, and mathematically it is. We just said so. It really, that's all you have to do, because it's a simple mathematical transform. So that now the irrational number is on the radius. That's not normally what is wanted. That's not what science has used. But you can do this. It's just that it looks like it doesn't lead anywhere. Oh yes, it does. And we're going to see that right now. It turns out that by unitizing the circle itself, you can attempt a guess at what that might mean. It's not a line, so it doesn't have a linear value. Even though it is said that you can measure distance on a circle, that's a direct contradiction of terms. So what you're looking for is the equivalent of distance on a surface. A line does not have a surface unless you consider the quantization of the points but that's actually not a surface, and that's the great failure of Georg Cantor and Dedekind, who are trying to continuize the straight line so that it would behave as if it were a continuous object. But it can't be if you're going to have distance. You have to quantize the line to get the metric for linear spatial separation. That's called quantization. You have to make a unit and divide the line into units for any distance measurement, which also requires a 0. Now, it turns out what I've been able to prove is that in circularized space, which is what this graph shows, with these concentric circles, that's the circularization of the plane. If you can give values to the circles, because that will be the equivalent in circular space of linear distance, instead of going from 0 on a straight line to a single component point. You go out on a circle, which is a two-component object. It's a two linear component object. It can be parameterized that way. Well, instead of using the Pythagorean theorem, which uses the linear operator add, there's actually an operator for circular space, an operator for the circle, instead of for the line. The line uses add. But what about multiplication? Multiplication, the way it's taught to us, is an independent operator, just like add. But that is absolutely not true. Multiplication is a completely different operation geometrically. The way it was taught to me, and I know from having checked some textbooks, the way it's taught to everyone is that multiplication is repeated addition. That's the biggest blunder of all. That is not what multiplication is, because of the inverse of multiplication, which is, what would that be? If multiplication is repeated addition, then division, which is the inverse of multiplication, should be repeated subtraction, but that's not what it is. So what's the error in that system? It's that add only works for the line. But for the closed line, the perfect closed line called the circle, you can no longer use add. Instead, you use a special two-component number form called a proportion, and the way the proportion is written is as a fraction, such that, for instance, 1 over 2, probably the most famous and simple fraction, is 1 over 2, which we say as 1/2, because we think of it as division. But again, that is actually jumping the gun on what's actually happening. If it were division, you're dividing the object into two parts. Well, you do the same thing with a line. You divide it into parts. So there's nothing strange about that. However, how do you do division? It looks like it's an operator that takes two arguments, which is true. But then what do you do with them? You do the inverse of multiplication. Is that true? Yes, but what does that mean? If you have the function div, which is how programmers would write it, and to write the function signature, you have two variables. And this is true for all four operators, although subtraction really is not needed for distance. But subtraction is a useful operation, of course, and it's perfectly legal. It's just that it's non-commutative. You can't subtract the same way that you add, because you have to designate which number comes first. In addition, you don't. And it really is different to add 2 to 1 than it is to add 1 to 2. It's just that numerically they're identical, but geometrically it's not. And if you actually draw it out on a line and do the separate steps, perhaps by drawing with colored pencils each step, you draw the blue dot for 2 and then draw a red line to 1. For subtract, you draw a red line to 3. You do the operation on the line and you show the steps. But if you start at 1, that's now the blue point instead of 2. It's just that the numeric result is identical. So that's quite a useful shortcut to know that. It's called commutativity. Well, you can't do that in subtraction. It's not non-commutative. And what does that mean? It means that when you take the inverse of an operator, you have to be sure that it's invertible. In the case of addition, it is. But if you want to have closure in your system, you'll have to have negative numbers. But really, that's the only hitch. And once you do that, it works. So subtraction and multiplication are taught to us as additive inverse operations. So that add is the operator and subtract is the inverter. It does the opposite. But then you have to use the right order. Whereas it didn't matter, you thought. In adding 3 to 2 or 2 to 3, you get 5. But then if you want to subtract 5, 3, you have to designate which number comes first. For distance, it would have to be the larger number, so you end up with a positive distance. Otherwise, you're not measuring distance. There's no such thing as negative distance. But the way mathematicians manipulate numbers, it's perfectly lawful. There's nothing wrong with having a negative number. You do have to be consistent. And remember that subtraction is non-commutative. Now, in the case of multiplication, in the case of multiplication and division, these are considered to be multiplicative inverse. But of course, the numeric relation in the inverse is quite a bit different. On a line, if you go 3 forward and then go 3, how should I say this? If you add 2 to 3, you reach 5. And then if you invert that, basically using convention of the same order, you use the result first because it's going to be the greatest number, and subtract either one of those numbers, 2 or 3, you get the other. So that makes sense. Now that's perfectly reasonable. Now with multiplication and division, though, what happens? Say you have 1 over 2. Well, what's the opposite? That it would be multiplication. All right. So 2 times 1 is 2. But now what do you do with division? Again, order matters. But is it the same relation in the result as with addition? It's quite a bit different. And here's how. When you have addition, with or without subtraction, but we'll say with subtraction because we're used to that. So now you have a double ray. For every one you go positive, you have a reflection on the other side, and that balances. And the balancing number is 0. that was discovered later. Euclid actually didn't know that. They used neither negative numbers nor 0. I may have to curtail this because of my allergies. The sun has come up, and this is actually considered to be the worst time of day for allergy sufferers. But I do want to complete this at the expense of my voice and your patience, perhaps, so we get closure before the next video. If you say that a circle is a two-component object, which it is on the plane, any position on the circle will be a coordinate number, of course, an x and a y component. And it's very interesting to keep contemplating the extreme difference between circular space and grid space, which is kind of skeletal. It doesn't really get everything on the plane. That's a broad statement, but let me give you the comparator. If you have circular space, where here the origin is still what you would think of as a point, but in this case it's the only point in the system. There's not two endpoints. There's only a center point. And that point itself cannot be a circle because it doesn't have a surface, if you're saying that the center is a point, which we're not. We're just saying it's the center of the circle. We're used to saying that that's a point. And that's reasonable for now, but remember, that would be a linear point. a point, a Euclidean point. So you could say the center of the circle is a non-Euclidean point. But you would have to prove that it's non-Euclidean. I've actually proved that it's superpositional, which you would expect since it's the exact same point. For the center of a line, you can see it. This O, that's not a zero, but an O. For each of the two lines, the vertical and the horizontal, of course, the numeric value of that point is 0 for both aspects. So it's a double 0 on the plane, because it's a coordinate 0. It's 0, 0. So it is a two-component center. And it's not a Euclidean point. That's obvious, because it's not on a line if you define it that way, but then you can go back, as I did, in the antipodal theorem, which I'll show you, although it's in my previous videos if you want to look it up. By that title, you can look it up. I've given several presentations on my original theorem, which simply relates an infinite line to an infinite circle. It's the infinity that's so critical to capture. And I'm going to change gears here because I think you understand. Okay, let me put off talking about what I was about to start in order to complete the prior thought. A circle, being what it is, as we've discussed, cannot have a distance value. You can't measure the length. You can pretend, and you can try, and you can lie to yourself, but that's not what you're doing. You want the value of the whole thing. In other words, the object has a value. It's a number. It's a two-component number. But what would that be? It would have to be the composition of two linear numbers. Well, let's say you unitize both the vertical and horizontal aspect to do what basically is to get a unit circle in two-component space. In other words, we're going to combine x and y not with addition. We want to combine x and y with the other operator. But which one? Multiply or divide? It's actually divide, because it's a proportion. And a fraction, if you define it correctly, can be defined as a proportion. Which means what? It's a relationship which is expressed as a fraction, such that 1 over 2 is the relationship of unity to the number 2 when 2 is acting from below, so to speak, which we call dividing by 2, which is accurate. I'm just trying to get you used to questioning the terminology, because sometimes you're going to hit pay dirt. You're going to go, that's not the right term to use. I've pointed that out several times in some cases as we've approached this critical turning point, because we want a number system for the plane that does not use add and does not use the Pythagorean theorem. We want to combine the two aspects multiplicatively is the technical way to say that, but that's misleading. It's actually, you want to combine the numbers so they're proportional. And I'm going to give you a key insight, which I'm not going to attempt to prove, so this might challenge you, but it is true, it is proved. Oh God, this is always a dangerous thing. You should really trust me now. It's going to sound strange. Oh, sure. Setting you up for the kill. It's a rate, okay? It's a rate. And in fact, when Newton defined the differential calculus, it was as a rate. He's trying to get the exact rate of change. It's in all the calculus textbooks, so I'm not making this up. But what is a rate? It's a fraction. When you when you take a calculus derivative on, for instance, just a simple sine curve, which is a curve, but it's a special form of curve called a sine, sometimes called a sine wave, which is simply an undulating curve. Well, it has a formula, so you can compute any position on that curve. But it's going to be a two-component number because it's on the plane. Well, same thing with a circle. It's not a line. Which is only half on the plane. You need two lines to even see the plane. But with a circle, you see the whole plane. And I think that's about all I have energy for. My voice is, I'm forcing it out. So rather than torture you, I hope you're getting something out of this, but we'll pick up where we left off when my voice recovers. And thank you for your patience, and I do urge you to stay tuned for the next video. I am going to make this go so swift, it'll blind you. Well, you know that so far, for over 1,600 lectures, I've been virtually incapable of speeding my pace. I don't think it can be sped up. I know it can. I'm not perfect. But bear with me, because I'm a young scientist. I've only been discovering all this secrets in physics, mathematics, and the universe for only 4 years. So don't expect too much. Thank you to all my listeners, especially my commenters. I love getting comments. Very rarely do I get anything that even suggests either stupidity or callousness or just anger. Yes, very rarely. And when you do, that's the way the ball bounces. There's all kinds of people, and you're not going to rub everybody the right way. You're not the universal panacea of just the greatest chum in the world. There's going to be somebody who just thinks that you stink, whereas nobody else does. So you get a criticism, let it roll off your back. What you do need to observe the tone, though, because sometimes you can actually address an angry question and perhaps even achieve conciliation. It's like, I noticed that you're angry at this, and I just wanted to just point something out to him, and then you might get a reply. Now, this doesn't happen to me because I don't get bad comments, but I don't get a lot of comments at all. Anyway, there's always a way to make peace, and that's the way of Islam. That's what I am trying to learn. May Allah bless you on your path by all the names of God in any language and any idea of universe. There's got to be a great creator, otherwise why are you in anything at all? So keep looking up, and we'll be right back. Sorry about my voice. I promise I'll be back. Stay tuned.